Thank you very much. I'd like to thank the League of Women Voters Bay Area for this opportunity. It's an opportunity I always enjoy to give the scientific, specifically geologic perspective on climate change. So we'll just jump right in. I have a background in geology, a PhD in geology, worked in the oil and gas field for 23 years and continue working in a variety of areas scientifically, but always focused around geology. For the topic today, the first question is the climate warming. And the answer is yes, it is. These are data from the Intergovernmental Panel on Climate Change. And although these were from 2007, the data haven't changed. That's the beauty of geology. It doesn't change over time, although we get more precise. And you can see that the temperature is increasing. The global average sea level is increasing. And the stage that we're looking at is from 1850 through 2000. Most of the increase is from 1950, actually even more recently than that. Also, the North American snow cover is decreasing. So yes, the climate is warming, and associated with it, we see expansion of the oceans and loss of snow. Now, geology. These are data from ice cores from Antarctica, from the thickest part of the ice sheet around Vostok. The core itself looks like this, and a worker working on the core in the cold down in Antarctica. You can get from looking at ice cores time, so we range from today to 800,000 years ago, 800,000 years ago. We can measure the amount of CO2 in the atmosphere, the temperature at the time, and the amount of methane. First thing to notice is that they correlate. So where CO2 is high, temperature is high, methane is high, and so on. And there is a very good correlation. We don't really understand the correlation. We don't know why methane and CO2 couple. We do know that when CO2 and methane are high, temperature is high. One thing to notice, this is 800,000 years, 800,000 years of data. We've only been existent as a species for less than half of that time. So this is geologic data. All of history is within this little tiny splotch right here. So all of human evolution, and certainly all of our civilization, is well within the end of this plot, where we've been about this temperature. In this period, CO2, the highest it ever got, was about 300 parts per billion by volume. Today, we're at 387. In other words, significantly higher than we ever were in that 800,000 year past. And it happened fast. On a geologic scale, it's much smaller than the width of the line there. Throughout that period, methane, at its peak, was about 800 parts per billion by volume. And today, we're significantly higher. Temperature at those same peaks. So at any of these peaks, you can see they're somewhat similar. The maximum is about 4 degrees Celsius. That's about 7 degrees Fahrenheit. And we're always measuring it over the average of 1950 or the years averaged around that as 0. So 4 degrees above that. The temperature today is only 1 degree above the 1950 level. And why is that? Why has the temperature gone up more? A couple of things to say. These are geologic data. The error around the points is something like 200 years. But clearly we would expect temperature to be coming up. To understand that, you need to understand a little bit about what's causing the warming. These are data from, again, the Intergovernmental Panel on Climate Change, showing something called radiative forcing. Watts per square meter. A watt is about the size of a Christmas tree light, a square meter, about a yard square. Radiative forcing is positive warms. So the red lines, the plus side of this shows things that cause warming. Big on it is CO2, which are the long-lived greenhouse gases. Methane is significantly smaller in volume, but it has a larger impact. Halocarbons are even smaller in volume, and they have a significantly larger impact. So you add that, plus that are warming elements. Ozone depends on where it is, if it warms or cools. Surface albedo, whether it reflects or absorbs. And then there are these two. Total aerosol, which is the fine particles that we put into the air. Pollution. Could be contrails as well, that's separated out. But the direct effect is shade. When it's a cloudy day, it's shaded, it's cooler. The next effect is the cloud effect. Little particles provide a nucleus for water droplets to form. And they're, in this case, much smaller than the average droplet, and so they're white clouds. So these reflect the sun and cool. So it's shadow and clouds reflecting the sun back. So you see that when you add it all up, the radiative forcing is less than it would be if these were all just positive. So we're not warmed as much as we would expect, based on the greenhouse gases in the atmosphere. The challenge with that is that these critters stay up there. This is about 200 years. These can be tens of thousands of years. This is much less, like 20 years. But on average, centuries. They're up there for centuries, 200 years. These are up there for weeks. On 9/11, we stopped flying planes, if you remember, and we noticed the temperature go up. That was just from contrails. So climate change is now. We have, relative to the maximum we saw over 800,000 years, we are significantly higher in CO2 and methane, and temperature not as much, but we think we understand why. Something to notice is the amount throughout this period we call the Pleistocene, the ice ages. The amount of change is way beyond anything we've seen before. But particularly the rate of change is significantly higher than we've seen any time throughout geologic history. And we really don't know what to expect and when to expect it. We have ideas and we're learning every day, but it's important to remember that this is something, it's unplowed ground here. Some of the evidence that this is happening, we see melting of the ice sheets. This is Greenland. In 1992, the extent of melt was in this area. In 2005, it's in this area. If you look at the data from 79 to 2004, yes, it's up and down, but it is melting. Total melt. The importance of Greenland and Antarctica as for the human population is that it causes sea level to rise because the ice is on land. So when it gets off land and into the ocean, it can cause sea level rise. It will cause sea level rise. Antarctica is also warming. This is showing average temperature change in this period. And anything that's a yellow or a pink color is warming. The blues are cooling. So there are parts that are cooling. Palmer Peninsula is warming significantly. This little critter is a chinstrap penguin. I got to go to Antarctica this February. And the anecdotes from the folks at Palmer Station are that, boy, things are changing. The data show that too. This is Antarctic mass variation from 2003 to 2009. It's decreasing, the ice mass. And there's evidence of it. This is from 2009. There's an ice bridge here on the Wilkins Ice Shelf, and it melts away. 2002, we had the collapse of the Larsen B, a big piece of the Larsen B ice shelf. So we're seeing melting in Antarctica. This all causes concern for sea level rise. So far, the sea level rise we've seen is mostly because of thermal expansion of the oceans, but it seems to be going faster. These are data from 92 to 2004. We're at about 3 millimeters a year. That's about an inch, a little more in a decade. Not very fast, but it's faster than it used to be. It's about twice as fast. And we haven't really put a lot of ice in from the ice sheets. Sea level rise in the last interglacial, which was when it was warm on those plots we saw, was 4 to 6 meters. And that was with maximum CO2 concentrations of 300, 4 to 6 meters. We're now at 387 and going up. So we don't know when that's going to happen, but it will happen at some point. The prediction, one of the latest predictions, and it's based on this work down here in Geophysical Research Letters, is about 1 foot by 2050. But storm surges related to that, according to FEMA, are significantly more destructive, and every additional foot will cause more damage. So the insurance folks are a little bit worried. The people involved in this is interesting. If we have 1 meter of sea level rise, 100 million people are directly affected. That's a lot of folks. And many of them are in low-lying areas like Bangladesh. If we have a 3 meter sea level rise, there goes New Orleans, there goes the places I work in Mexico, there goes the Keys, southern Florida, and so forth. That's 3 meters. We were up to 4 to 6, round numbers, in the last interglacials. So geologically, is this a big deal? No, not really, not a big deal. Much, much worse has happened in the past, but remember, we didn't live then. So from a human perspective, it's a slightly different thing. This is a temperature plot from these folks, Crowley and Kim, again, Geophysical Research Letters, showing the change in temperature relative to 1950 again. So we get up to 6 degrees kind of range, and that was what we call a greenhouse world. It was when the dinosaurs lived, and you've seen Jurassic Park. They were extinct about 65 million, and we were cooling during that period, but temperatures were in the +5, +6, plus almost 7. This 5 should be right there, I think. No, it's right where it is. In any case, we get some Antarctic ice forming in this period, but the persistent, or the ice that never leaves, is at about this place, and we're 2.5, 3 degrees. And then the northern hemisphere ice sheets that you think of as the glacials were within the last 800,000 years, and we saw that in the ice core data. Looking at sea level, we just talked about this, so that's the last, and interglacial. In the Pliocene, so-called, the 3 million years, it was significantly higher. Pliocene, at 3 million years, is right here. So don't forget, from a human standpoint, these are millions of years. These hundreds of years are the thickness of that line. These are predictions from the IPCC. We don't know where we'll go or how far we'll get, but we're getting into ranges of temperatures that are significantly high, certainly from a human perspective. We've talked about sea level rise. Melting of Arctic ice is another issue. These are model data from the Geophysical Fluid Dynamics Lab at NOAA. Back model to 1885 and 1985, forward model to 2085. So we're losing Arctic ice. Now, Arctic ice floats on water, so it doesn't raise sea level. So does that matter? For the wildlife, of course, we've heard about, it also gives you an open passageway and opens up all that for oil exploration, for trade, and so forth. The data from 78 to 2011 show the average Arctic ice extent is decreasing. We had a hiccup in these years when there was a bunch of articles saying, oh my goodness, it's decreasing faster than we thought, but then it came back. Word of caution, when you're dealing with geologic phenomena at a human scale, you need to be careful. Why should we care about Arctic ice though? And it's because of these little critters called methane hydrates. In the permafrost, methane is trapped in ice. In a cage structure called a clathrate or a hydrate, these are water molecules, the red, and it's a cage of ice capturing a methane molecule in green. There's a lot of methane hydrates, tons of methane trapped in hydrates in the permafrost. As the permafrost melts, the methane is released. Now, methane is a potent greenhouse gas, and there's a lot of it in permafrost. This is actually ice. It's very famous in geologic circles. It's burning ice. The ice is melting, the methane is being released. You light a match to that, and the ice itself burns. These are clathrates. They're not really, it's an ice structure. So that's why we want to be careful about losing the Arctic ice. How much is that really? This is the purple up here looking straight down on the North Pole. The purple is area of permafrost, 8.8 million square miles. And we're talking about a very large number, carbon as methane and CO2 being released. And an estimate from these folks that would bring on an additional 3 degrees C over and above what we're looking at. So that's one of the tipping point things we need to be cautious about. So how much might it warm? These data from the IPCC, 3 scenarios. One is if we were able to stabilize at 2000, which we haven't done. One is if we stabilize by 2100 at 550 parts per million, which is doable. And one if we continue like we're doing and stabilize but at 700 parts per million. In the next 10 to 20 years, we'll be seeing in all models 1 to 2 degrees in the northern hemisphere. And by the end of the century, the last half, as early as 40 years, maybe up to 7 degrees in the northern part of the northern hemisphere, and 4 to 5 in all the continents. Both of these are fairly severe, and it looks like we're on track for one of them at least. So what does 4 degrees mean? Based on what we've seen, if we have a 4-degree temperature change globally, we certainly will see changes in weather patterns. It changes the ocean currents, changes. We've seen change in weather patterns even recently. Water scarcities, possibly fires, food shortages, famine in places like Bangladesh if they're above water. For us who are more fortunate, escalating food prices. Significant extinctions, loss of biodiversity. Rising sea level, how high and how fast, we're not sure. Certainly a threat to security, global stability. So it's not something we want to go toward. So how did the CO2 get there? These are data from the US. 83%, almost all, is from fossil fuel burning. Lots of other things, but they're much, much less. These data are similar for the world. It's about 80% fossil fuel burning, and land use is higher. So mostly emissions from fossil fuel combustion. We're good at it, we people, and just to say that we have reached geologic proportion as a civilization. It is now proposed that we are in the Anthropocene. A formal epoch means the age of man. To be a geologic epoch, this is real, to be a geologic epoch you have to have a change in biota, sedimentation, geochemistry. And we've done it. And here we are. You can see that the sedimentary record is going to reflect all of our land use, cars and so forth. And the chemistry of the ocean, chemistry of the atmosphere is changing. So this is where we are today, and we're growing. So we are the ones that are putting that fossil fuel emission into the atmosphere. This is U.S. energy consumption from 1950. Nearly everything is fossil fuel. Some nuclear, some renewable. This is up to 2008. So a large amount. We're flattening in our use, which is good. This is flattening, but U.S. energy consumption, global energy consumption. Asia particularly is growing remarkably, and their per capita use is growing very fast as well. And it correlates with temperature. So what should we do? Two things. We need to reduce greenhouse gases, and we're going to have to adapt. We don't know how far or how fast things will change, and it doesn't mean that the ice sheets are going to all melt. The temperature went up and down and up and down in the Pleistocene, that 800,000 years you saw. We never lost the ice sheets, and we got to peaks of 4 degrees C. So we don't know, remember, we don't know what's going to happen, but we do know we don't want to continue on this path. Reduce greenhouse gases. The low-hanging fruit is energy efficiency, conservation, and getting better use out of the fossil fuels we use. Efficiency standards, and have benchmarks and control to it. Put the power of the capitalist system to use by putting a price on emission. Whatever way you do it is good. I personally favor carbon tax. And it needs to be a global solution. It's a global problem, it's a global solution. And a lot of people already are working toward that. The United States is somewhat trailing. So we need to get on board and move in that direction. So we can do it. We don't know where we're going, but we do know we have to reduce our emissions. We can't continue on this path. So thank you very much for the opportunity, and I'll entertain questions.